1, 2, 3. Great. Okay. Well, thanks to Millie and the co-organizers for organizing this workshop. I particularly like the sort of size of this meeting. You know, these huge annual professional meetings we go to with thousands of people. I just find myself getting relatively little out of them, whereas in small groups like this, we can, I think, tackle, or at least express some of the challenging and kind of open questions that are bothering us. And that's a little bit the sort of spirit of my talk. Millie sort of asked me to give some background, but I didn't really want to give a pedagogical talk. In fact, I've given so many of those. I'm kind of tired of hearing myself speak. What I wanted to share with you, though, are some real puzzles I'm having. So there's a little bit of a kind of a personal take in the issues I'm going to bring up, and it's sort of asking us, why do we do what we do? For example, we tend to like to think that, and this is maybe a prejudice of a physics training, that there are simple rules, universal laws that describe the world, and that guides a lot of our thinking. And you can go back even to Newton's Principia, and he's particularly pointed about this, that, without citing Occam actually, that we should use somehow the right models are the simplest. So that's a little bit the theme here. I want us to think about that, and I hope it kind of generates some discussion throughout the week. I'm certainly sympathetic to this training, but I'm struggling with it. So I want to talk about how this notion of simplicity is fraught, how it's not quite so simple, and in fact, even the pursuit of it can kind of backfire on us. So my comments will be sort of conceptual at this level, not a lot of mathematics, although hopefully the ideas are interesting. And the way I'm going to frame this is think about the tools we use, the conceptual tools that we have come to use to describe a complicated world out there. And so the first question is, why do we use information? What is information? Why do we use it? So I'd like to spend a few minutes meditating on why maybe some of us, a lot of us, have turned to notions of information, in particular from Shannon's information theory, and kind of explore that a little bit. But first, what are the motivations? The use of information in the sciences, and this is going to be a theme throughout the whole talk, has been around for a really, really long time. In fact, I've spent quite a bit of time over the last 3 or 4 years puzzling over these issues, going back and reading a lot of the original texts and the original thinkers on this, whether it's von Neumann or Wiener, Shannon, the early cybernetics movement. There's now some very nice historical books coming out by serious historians of science probing this. They're very strange political influences that govern why we're even here in this room, having to do with the schism between the East and West and political economies and design of economies, whether or not even the word cybernetics shows up in Western universities. It certainly doesn't at all in the United States, and that is due to a political reason and also some personal improprieties in the early founders. So there's really a very long and interesting history, which I recommend to everyone. It's certainly given me a lot of insight and maybe kind of allowed me to start thinking about foundations a bit. I mean, often if you read something in a textbook, and students are really bad at this, you take it at face value. Hopefully some of us, at least around for a while, you start going back and sort of thinking about these assumptions we hold so near and dear. And that's a little bit the meditation today. Now, the particular take I have on the use of information theory in, say, physical or biological systems really goes back to Kolmogorov. That's a name. It shows up in so many different domains. And his student, Yasha Sinai, who kind of borrowed or moved Shannon's original information theory, which was introduced in the late 40s, into being a legitimate physically well-founded analysis approach in the late 50s. So that was, up until that point, there were a number of technical problems with using information theory directly, although people were rather enthusiastic at the time in the 50s about this, which even led Shannon to write various polemical articles telling people to sort of tamp things down a little bit. That's not what I originally intended. But anyway, Kolmogorov and Sinai are actually responsible for bringing information theory and showing it had a well-defined mathematical foundation in physics. This is not generally appreciated. This work, though, had a profound effect on the area kind of foundations of statistical mechanics we call ergodic theory and dynamical systems theory. So although it's not part of a traditional physics curriculum, the connection with information theory and physics goes back, at least I'm willing to argue for. There's more history to read, but that it kind of turns on these papers in 1958 and 59 by Kolmogorov and Sinai to show that information had a basis, a good physical basis, was consistent with it. Now those papers are fairly mathematical and not immediately accessible. But anyway, this has grown. The suggestion that somehow Shannon's mathematical theory of communication is relevant to physical and biological processes is something that's been going on actively ever since. In fact, preceding Kolmogorov, even from the late 40s, immediately after Shannon published his papers on this, there was just an unbelievable efflorescence in the use and thinking about information theory, sometimes called cybernetics. It turns out in England, for example, cybernetics was called information theory. In the United States, it was called cybernetics, which by the end of the 50s was politically inappropriate because the Soviet Union had borrowed Wiener's cybernetics and the philosophy of it to start rationally designing 5-year plans. And of course, in the United States, by the late 50s, there was this huge shift to the right. Historical resonances here. Huge shift to the right that found all things Russian, Soviet, or communist as inappropriate.
That happened only around 57, because before 57, cybernetics was a whore of imperialism.
Exactly, yes. Well said. I wouldn't have used that. Yeah, the history is, okay, we want to make scientific progress, and we're going to get into some technical issues, but I do find now the kind of sort of social and political background really fascinating. It informs a lot, and it to me, you can see where there's certain barriers for progress historically. Maybe that suggests things that we should think about overcoming, but anyway, I could teach a course on the history of cybernetics and information theory. It's fascinating. Okay, so, but let's think about the conceptual realm. We're scientists, we're purists, we don't want to get sullied by social political things. So why information? Well, for me, it's this. It's the fact that the world likes to form patterns. Doesn't matter whether you're looking at fluid flows here, so this is a series of 4 experiments where there's a cylinder here, fluid is flowing past the cylinder from left to right. In each one of these, the fluid velocity is increasing, going down, and what you see is that different experimental parameter settings, different fluid velocities, you get this increasingly more complicated looking flow pattern. We're visualizing this because the cylinder has a little hole that injects ink. And what you see is it gets more complicated. Well, the question is it more complex? But anyway, we have this instability here. End up with these actually singularities as you move down in the flow, as you move downstream, those turn into vortices, and then at sort of high flows, you see this, what's called the von Karman vortex street. Theodor von Karman was the first sort of hydrodynamics theorist to describe this flow pattern. But there are other domains. So we're looking down here at the sort of famous Belousov-Zhabotinsky reaction, Petri dish with 4 reagents in it, and if you pour these reagents in and you wait for about 5 minutes, suddenly every little volume fluid element starts reacting and oscillating. And then what happens is that certain regions get synchronized, and those correspond to these apparent waves that are moving across here at about kind of that speed, correspond to this emergent organization, and then you can see at a kind of a higher level there's interference between them and so on. So I'm sure some of you know that this work, when it was first done, Belousov and Zhabotinsky tried to publish this in the Russian chemistry literature, and it took them almost 10 years because, well, there was a whole series of excuses. First of all, this is not possible. Why? Why is this not possible? Equilibrium. This is not an equilibrium. This is not possible. Rejection. Just to give some of the young folks some heart. So, and then, which is weird, right? You're publishing an experimental paper with the recipe. That means you can all go, at home after reading, physical chemistry journal, and I won't say it in Russian, and do it yourself. But no, it's not right. Next round was, yeah, okay, but it's a transient, therefore it's unimportant. That's true. If you actually wait for half an hour, the oscillations slow down, the waves disappear, and it stops. Uninteresting, right? That's this odd. Is this a rationally justified value judgment? Interesting how value judgments can come in and color whether it's good science. So eventually published and actually formed a really critical report on self-organization phenomena that in the early 60s was finally started to be analyzed by a couple mathematical biologists. And then also connected up with Alan Turing's earlier work in the 50s on biologic morphogenesis. And that led to the modern theory, now called pattern formation theory or center manifold theory. So there you go. Anyway, nature forms patterns. Now, so far, I won't explain the rest of my favorite things, but what have I been doing in describing these? I've been using English, human language, calling on your built-in vocabulary to maybe kind of understand the patterns that you're seeing here. That's not really fair, is it? Imagine that we didn't have a vocabulary. Imagine now that we're looking in the world of big data. We have so much data, so many degrees of freedom, in so many high dimensions, or we don't even know what the dimensions are. How would we come up with an analogous structural description? Or to say it another way, imagine that in the BZ reaction, this chemical oscillation, I gave you, at every point in space and every time, the concentrations of the 4 reagents. So here, I'm going to give you this giant thumb drive. There's the data. I don't tell you anything else. How would you come to know that there were oscillations? Well, you can, I got that. I listened to my introductory physics. I know Fourier transforms. I would Fourier transform the time series from a point. Then I would see what's oscillating. But then how would you notice that those oscillations eventually became phase-locked, that they were advancing, that they formed these target spiral patterns, and that there was constructive and destructive interference, that there was a particular wavelength even? So that's sort of the question. How do we do this? And so the claim here, the implicit claim is, it's not really a story about energetics. Energy is important, but it's really a story about the relationship between degrees of freedom and their behavior. So, so hopefully information theory can start to describe some of these different kinds of pattern formation. Happens. So what tools are we going to use? And this issue of pattern and structure is just, it's very common across the disciplines, maybe even more important in some ways in biology than in physics. So here's a nice picture of the structural hierarchy in biology, right? So you start down here with simple molecules. Those form to make larger molecules that make these super macromolecules like DNA, or complicated things like proteins that are functional, and so on. Those form into things that make single-cell organisms, various kinds of tissues, and so on. There's this kind of very natural hierarchy of structure. So again, I ask, how are we distinguishing these different levels of structure? Well, it's a little bit sociological, right? There are different areas of biology, going from molecular biology to biochemists and up to field biologists and so on, that have some realm that they consider themselves experts in. And we end up with this picture that there's a hierarchy. Things are built out of things. But then we move from one level of organization to another. So first question, how does nature organize? And what mechanisms that produce this hierarchy? Are these levels really sociological, like I just said, or at some kind of convenient thing? Or they actually have an ontological status, a physical fact or biological, some future biological fact? And then what's driving all of this? It's a little too facile to say evolution. What is evolution doing? Why picking these things and not others? Is it all historical accidents? This is a very famous debate in the 80s and 90s. Is it all somehow adaptation to some goal, teleological reasoning? Is it all constrained by physical, chemical, mechanistic laws? Notice where this picture appeared, Physics Today, right, the monthly APS magazine. So why was this in the physics? I look at this and I think to myself, again, highly prejudicial personal opinion, the whole hierarchy itself is a question for physics. I think explaining the entire hierarchy, its emergence, what levels you have, is really a question in physics. It's about biological facts that biology has taken centuries to accumulate, but the fact that there are these nested levels of structure, I think, is a problem in physics. Or the other way is, boy, we have got a lot of homework to do as physicists to even begin to approach this notion of nested hierarchy in this kind of hugely ramified way. It's no shortage of open problems. Okay. There are other domains. Let's move back to the chemical domain. I want to puzzle you with some things. Examples of phenomena, kind of interesting. Oh, why do you find them interesting? Well, here's one. So again, Petri dish. There's this kind of thin blue liquid here. It's only just a few millimeters thick. I won't tell you there's some reagents in there. And then we're going to stick in a little oil drop of a particular composition. This inanimate system is like moving around, moving through some environment, actively motivated. Also, when its environment changes, it changes its behavior. It's adaptive. Is it alive? How is it working? How smart could this be? Oops. So again, I could give you all the data for this. Here it is, the video sequence. And how would you, what would be a good explanation for this? What's going on? What's interesting and curious? How is it structured? How is it random? How do those two things balance off each other? So another example. So again, looking down a proverbial Petri dish, layer of water, and we have these small nickel spheres that are floating, kind of peppered around here. And what they've done is they put an in-plane magnetic field, oscillating at several hundred hertz. And what happens, I can't imagine how long it took them to figure this out. But anyway, what happens is this structure appears spontaneously, this kind of segmented structure. And you get this little wormish kind of thing that actually motors around the Petri dish. Huh? I mean, well, my hat's off to the experimentalists. I can imagine tweaking the magnetic field and how they had this idea, and then to see this, it must have been one amazing day in the lab, right? It's moving. And it's interesting. It's structured. So what's going on here? How do you explain that? How do you explain that? So when I look out at the world, when I think about the kind of richness and complexity of the world, my question is not so much how does this phenomenon fit into what I currently understand, but how do we ever discover something new? So I call that pattern discovery, to sort of make the distinction with pattern recognition. Voice recognition systems, like when you call up Singapore Air and you say, I want to go to Singapore in the state, you're talking to a machine that has a built-in vocabulary. That, to me, is not the essence of science. It's not this issue of discovering new things in the world. The question of pattern discovery is, how do we extend our vocabulary And we need to do pattern recognition to certainly recognize what's already known. But what about how do we extend things? How do we discover new structures? And a little bit, I'm sort of, the implicit argument here is that maybe information theory can kind of help us with that. So this is a favorite quote of mine from the structural sociologist Claude Lévi-Strauss, linguist, from his trip in 1930s into the Amazon basin. And I like the last quote. Well, the main idea is this is a common experience we've all had. You're starting a new theoretical problem. You go and you start reading literature. I don't understand a thing. This literature is a mess. I don't understand. And then somehow, through trained persistence, we sort of, it starts to make sense. So Lévi-Strauss is talking about coming to the Amazon basin. He's going to study the linguistic structures of languages that the tribes use and how they're related and unrelated. And he just shows up. He says it's this terrestrial distemper. Well, then eventually he says that as soon as the eye becomes accustomed to recognizing the forest's various closely adjacent planes and the mind has overcome its first impression of being overwhelmed, a complex system can be perceived. So this, to me, is a very optimistic statement, that somehow what we do, well, as human beings, animals, agents moving through the world, but also as scientists, is we have this ability to do pattern discovery. And that's my kind of main interest, kind of philosophical motivator in my work, why we're interested in using information theory, talking about pattern, trying to be quantitative. So, and we need some principles to do this. Now, I have to admit, this is the kind of personal side, there's a very specific take I bring to this question. It goes back to hydrodynamics and fluid turbulence, which was rather interesting. It's a nice Physics Today article by Heisenberg in the 56, I think it is. And in the article, he's talking about, right, so the founder of quantum mechanics, he's talking about why fluid turbulence is the main difficult problem in physics. Fluid turbulence? Heisenberg? Fluid turbulence was his assigned dissertation topic in the 20s. Sommerfeld gave him this problem. He was publishing already. He was seen as this young terror, the young sort of card-carrying theoretical physicist working in this new area of quantum mechanics. But at the university in the 1920s, physics wasn't theoretical. It was experimental. Sommerfeld made him take a class in physical experiment. He nearly failed. So they gave him this problem, not in quantum theory for his dissertation, but in fluid turbulence. And this haunted him till his dying day. In fact, he handed in his dissertation on turbulence. Sommerfeld passed him with flying colors, and Wien, the local kind of grumpy experimentalist, failed him. He was so embarrassed by this that he didn't go to the kind of congratulation party for passing, but marginally passing, his exam. He immediately hopped on the train and went to Berlin to pick up his new job because he was afraid that Born wasn't going to hire him because he had done so badly. Like I say, our history is very colorful, interesting events and people and so on. So turbulence. So the reigning theory all the way up until the 80s was due to Landau that fluid turbulence was really just described by periodic motions, many of them being activated. And there was this alternative theory that came out of dynamical systems, a little bit due to Kolmogorov, that said, no, it's not just a bunch of these incommensurately tuned simple harmonic oscillators describing. It's actually one of these relatively low-dimensional strange attractors, these weird shapes. And so this question came up, how do I go from a high-dimensional system, like fluid turbulence, and figure out that there, maybe in some 7 or 8 or 13-dimensional space, is one of these abstract mathematical fractally chaotic attractors? How do you do that? So we introduced this method of extracting from a system's behavior an effective state space and then analyzing the behavior in that state space. That's the idea of geometry from a time series, the state space geometry from a time series. And so you can go from a turbulent fluid here, this is open surface convection, and discover something like this 3D attractor here. This is our 3D visualization system we use for some of these things. And then eventually did a careful experimental system that showed, in fact, that the Landau picture was incorrect for so-called weak turbulence. And it was, in fact, described by these nonlinear dynamics of these strange attractors. So So again, turbulence is hard. We didn't know what's going on. So this, to my mind, is a very concrete example of discovering something new. Partly started within the mathematics, going all the way back to Poincaré, who, through sort of free creations of the human mind, came up with this notion of inherent instability, deterministic chaos, that finally led to this resolution of the problem of fluid turbulence in low Reynolds numbers. So, okay, so that's kind of the kind of conceptual motivation. The world is complicated. It forms patterns. Somehow we seem to be able to, both as intelligent beings moving through the world or as scientists, able to discover new things. But how do we do this, and what are the right tools? So the question, is sort of working hypothesis, how would information help us? If the phenomena we're trying to describe aren't just minimizing some energy functional, these are behaviors in time, they're complicated shapes, what shape, weird symmetries, partial symmetries, how do you express those things? The idea is that information theory could do this. But there are also some really just very practical reasons what information theory shows up. One kind of directly addresses this question is it just as a tool, it sort of allows us to talk about any type of correlation. If you go back and you're well-trained mathematical statistician, there are various kinds of correlational measure, but behind almost all of them is some kind of linear model. And the systems we're talking about that form patterns are horrendously nonlinear. So any linear statistic from mathematical statistics is going to mislead you. Information theory can work with any kind of nonlinear correlation. And that has to do with the fact that, say, the entropy, different kinds of entropies, shared information, and so on, are properties of the distribution over the observables. And I'll assume most people know Shannon information theory. Is that okay, or is that not okay? Good, okay. But this is my 4-line summary of all of information theory. But we'll talk about it some more. The other thing about information is that many systems outside of physics, to take an extreme example, just simply don't have energy, right? You just can't do physical modeling, right? Whereas you can talk about information in social, biological, or engineered systems. You don't necessarily have to have, a kinetic theory of Twitter cascades to apply statistical mechanics. You don't need to do that. There's something else you're capturing, right? It's kind of subsumed in the notion of statistics, but then extending statistics so we're not stuck with linear models. Also, nice thing about information is the common units. If you use these various correlation measures up here, you're going to have meters, or volts, dollars, or dollars squared, depending upon what kind of measure you've got, ergs. Different systems have different units, and you describe their degree of correlation in these different units. They're not comparable. In information theory, we have bits. I mean, it's perfectly reasonable to compare the uncertainty as you're walking along a spin lattice, so your uncertainty in the next spin, with your uncertainty, the degree of uncertainty in whether the Google stock is going to go up or down. We measure that in bits. So the common units. There's also a very hidden but long history, started right after Shannon's introduction, Wiener's introduction of the basic ideas, this sort of interesting equivalence between probability theory and statistics and information. Cover and Thomas, Elements of Information Theory textbook has a nice hints at this history, but it's very active, mostly in the 60s and 70s, showing a kind of equivalence where appropriate between these different areas. But for me, information theory is mostly, the idea of information is mostly relevant because it seems to have a semantics of pattern and structure built into it, possibly, needs to be, that lets us talk about emergent patterns. Complex, nonlinear systems evolving over time, forming patterns in space. General complex systems, information theory is sort of kind of the candidate tool. The main problem being with these systems, sort of by definition, you don't know how they're going to get organized. You don't know how the BZ chemical waves are going to show up, or the von Karman vortex street, or animal coloration. So this picture, the sort of working hypothesis, reduces down to the idea that we can use ideas from information theory, techniques, concepts of information from Shannon's information theory, Wiener's information theory, to study the sort of storage and transmission and transduction of information. That, in other words, we can kind of use that as a way to talk about the architecture of information processing in a system. So, working hypothesis. Hopefully we'll hear this throughout the week, versions of this. For a long time, I was, still am, quite the advocate for this working hypothesis, but that's what I want to talk about. So let me describe a little bit how you can extend Shannon's information theory. And it's absolutely necessary. You can't take Shannon's information theory or even the kind of standard textbook information theory you find in Cover and Thomas's Elements of Information Theory and apply that to complex systems. It's not really up to the task because those basic theories deal with independent, identically distributed processes, just a few random variables, and so on. So you really need to extend the notions of information to deal with high-dimensional systems. In particular, what I describe is time series. How do we get to complex time series? Think about that turbulence experiment I was mentioning. You have a time series coming out. How complicated is the fluid, and how is that reflected in this time series? So fortunately, there's kind of a nice, it starts out visual, but a very nice mathematical property of Shannon's information measures, which I can show pretty quickly. This is maybe a little bit of pedagogy. So we're going to imagine we have some random variable, and you could kind of think of this circle here as the set of events, but what I'm going to do is actually, the circle is supposed to represent the amount of information that's contained in the random variable. So we look at the Shannon entropy of this random variable, and the size of the circle is the entropy of that. And you can think about another variable, y, and it has its own circle, all yellow here, and it's got a certain size. I should probably make these different size things. And so you can kind of build up this notion of different kinds of information measure using this Venn diagram, so-called information diagram, in a set theoretic way. So you can talk about the shared randomness or entropy between two random variables. It's these three things. You don't overcount overlaps. You can talk about how random variable x is if I know y, and that corresponds to a sort of set theoretic operation where I take the entropy of the whole random variable and then I take out y. It's as if it were set subtraction. I'm kind of misleading you here a little bit, but that's part of the fun. Same thing for y. We have a conditional entropy. How uncertain am I about y? When I find out about x, I have all the possible events of x and of y, and then I take out x. The information that's shared between them, the mutual information, is the intersection between these two. And there's even a very nice metric in the space of distributions, which is the sum of the conditional entropies. So every sort of piece here, the so-called sigma algebra atoms, this crescent, that lozenge, this crescent, has this information theoretic analog. And you can apply this to time series. So now we're going to have some process where there's a past, some present at time 0, and some future. So here in red, this is the past. And the notation here, this goes from minus infinity to 0, and we tend to drop minus infinity. And the future is this big green thing here, and we go from time 1 off to plus infinity. And the present is in blue here. So all of the information in the present random variable is this thing. And then what we do is we just intersect. We look at all possible intersections of these random variables. So it's kind of a generalized Venn diagram. And we see there are different pieces here. And these pieces are all interesting. They have kind of a natural semantic interpretation. So this is kind of one of the useful things about information theory. So how uncertain am I about the future if I know the entire past? Well, that would be the blue minus the red. So that would be this R mu plus B mu regions. That's the Kolmogorov-Sinai entropy rate, or the Shannon entropy rate of this information source of the process. What's interesting about this, and this is bizarrely a recent realization, is that this entropy rate goes back to Kolmogorov and Sinai in 58. It's just the last few years, we realized by doing this simple construction that it breaks down into two different pieces. So what Kolmogorov and Sinai introduced into physics, I'm arguing, is this notion that a system has a history and there's this irreducible randomness and uncertainty, unpredictability at the next time step called the entropy rate. There are two components, we claim. There's one component, RMU, that's information created in the current instant, but it's thrown away. It's not predictable from the past, it doesn't lie in the past, and it has no effect on the future, it doesn't lie in the future. Interestingly, there's another component called the bound information that's created in the current moment, but is actively stored by the system and affects future behavior, contributes to the future. It's a really simple construction. But it sort of, I would say, greatly enriches our notion of the rate of information creation. Some of that created information is thrown away, and some is stored and affects future behavior. And you can go on down here. There's a little wedge down here, sigma mu. That's the amount of information that's shared between the past and the future, but is not in the present. Huh? What's going on here? So this is actually related to the range of correlation in the system. So you start, instead of thinking of, I'm going to make a single measurement and that's my present, what I do is I make 2 measurements and 3 measurements. So now you imagine that the present is a block of length L, and if this time series was an order or a Markov process, sigma mu goes to 0. In other words, this present block information now exactly shields the past from the future. You capture the range of correlation. So this is sigma mu as a measure of how much, say, the single variable present doesn't capture. And so on. My point here is it's a nice tool. It greatly extends, it gives some new insight. It's almost, frankly, kind of mechanistic. You can sort of set up these problems and turn a crank. These things pop up, and you're going to go, what's that mean? And you've actually discovered something. So that's kind of fun to have the mathematics lead you forward. And you can go through and calculate these things relatively efficiently. So being from chaotic dynamical systems, we study these one-dimensional maps. This is the so-called tent map. It takes the unit interval to itself. And here in black, in the background, what we're doing is we're sweeping the control parameter A up here, which is the slope of the map, and looking at the series of iterates or points. And then what we're plotting at the same diagram over the same parameter range is the B mu and R mu. Well, most importantly, for the tent map, because it's piecewise linear, you can write down exactly what this Kolmogorov-Sinai-Shannon entropy rate is. It's just log of the slope. That's the degree of instability. It's positive when A is greater than 1. There's a little bit of instability or a lot of instability. But what you see, even though the entropy rate, information creation, is this nice smooth function of the control parameter as the system gets more nonlinear, in fact, R mu and B mu in the stacked plot, they add up to it, but they themselves are non-differentiable. Of course, if you stare at the diagram a little bit, you say, look, what's going on in this bifurcation diagram? There's all this weird veils and so on. Some of those are kind of implicated in this complicated structure. You can show that B mu must go to 0, these things called band merging, and you understand a lot about this. So the other way to think about this is that different control parameters, this system, it's creating information, but it stores it in different ways, in different amounts. B mu is changing. The rate of active information storage, B mu, is actually changing in this really complicated way. Interesting. A kind of information process, active storage. Is this useful? Open question. In fact, this whole information diagram, information measure approach extends to arbitrary numbers of random variables. So this was quite encouraging. My goodness, I can even start thinking about not just time series, which we're now looking at sort of infinite chains of random variables, but just think of like networks. Hundreds of variables at different nodes in a network. Maybe I can start to understand some of the information processing that's going on in networks. And so this nice Venn diagram, I won't go through this. There's this nice mapping between what's called assigned measures. Shannon's information measures are assigned measure over the space of events. And you can make this connection between different kinds of entropies, conditional entropies, mutual informations, and set theoretic like operations. In fact, it's just, there's even kind of a notational thing where you see H or I, you put in mu, the measure of the set. You see a comma, that's a union. You see a semicolon, that's an intersection, mutual information. And a bar, conditioning, is a set subtraction. So you can go through and prove all sorts of different kinds of identities purely set theoretically. So it's a nice tool. Why? Well, this all seems really simple. We're just showing down here what happens in two variables. It's kind of redundant, you know. I got it already once you work through it. But then you do have problems like this, where you have a channel where there's some input process and some output process. And so we talk now about the input process is past and it's future, and the output process is past and future. And what's the relationship between these? Well, you end up with one of these information diagrams that has 15 atoms. Well, when we first wrote this out, it was kind of like Levi-Strauss going into the Amazon jungle. It's like, Jesus, that's, In fact, I remember a couple of students going, I might want to work on that. That's too hard. But now, it's familiar. A complex system has been revealed. We can now at least drive around this diagram and interpret various things about it. So what I want to kind of talk about in the rest of the talk is not so much this rather detailed information atom analysis of channels. And these are general channels with memory, which we also don't find in the textbooks. I'm going to talk a little bit about this atom here that's received a huge amount of attention. This is called the transfer entropy. Notice that there are other atoms besides the transfer entropy. So there's this issue, right? Our working hypothesis somehow, at least some subset of people interested in complex systems feel like one way to understand how they're organized, how they're structured, is to look at where they store information, what kinds of information are stored, and how that information is transmitted, transported, and transmuted. So a key idea in this is information flow. This word goes back actually to the late 40s even, the earliest reference I found, the early information theory. People wanted to talk about information flow, notions of directed information, so on. So what is information flow? Well, here this concept is being used in the service of pattern discovery. I'm going to give you, again, think about that turbulence. I'm going to give you all the degrees of freedom, and you want to do some kind of statistical information analysis that will tell you how it's organized. 3 bits of information stored over here gets moved over to here and split in 2 different pieces and so on. So we want to detect the structure and organization by looking at the internal and external flows of information. Okay, so what do we mean by information flow? Well, this is a point of a good point for philosophical debate and discussion. Here's a suggestion. Information flow from some process, think of the channel, some process input to some process Y, the output. The idea is that there's information currently in Y, the cause of which you can solely attribute to X's past. I'll elaborate on this. So, and the key thing here is that the information being solely attributed to X, in other words, information showing up in Y, the output, but Y has been going on for a while. So we can have some information that comes from its own past. That would not be a flow of information from X to Y. What I want to do is say there's information to Y that comes from X, and uniquely so. Right? So we want to be able to localize this. Basically, blame X for this thing happening in Y. Okay, so one of the sort of first, a proposal was called the transfer entropy, was introduced by Thomas Schreiber in 2000, called the transfer entropy. So we have the transfer entropy from X to Y. It's the mutual information between current output and the inputs past, removing, in a sense, the information from Y's own past. Right? So you kind of see we're trying to capture here with this conditional mutual information the idea of something's happening of Y that's solely attributable to X. And this has had a huge splash. It has over 1,500 citations, pretty much 100 citations a year. Very popular outside of physics and neuroscience, econometrics. Hundreds of papers use this. In particular, maybe about half of that, a key point is that I can go into my data, my time series data, and estimate this conditional mutual information and understand the architecture of my system.
Sorry, just a quick question. The 0 to T notation.
Right.
That not actually include the T. Is this continuous time with
I didn't mention that. Right. So this, okay, inclusive, exclusive indexing. Sorry. Right. That was implicit in the time series thing that I did with, yeah. Sorry. Yeah. Sorry. Right. Yeah, that's right. You're right. So the present Yeah, okay, so maybe I should, this could be t plus 1. You're right. This implicitly, this goes from 0, variable x0 up to variable x minus 1, y sub 0, t minus 1, yeah. Sorry. Okay, so how do we think about this conditional mutual information? It's one way to think about it is how much better you can predict the output y using both x's past, the input's past, and y's past itself, compared to just using y's past to predict itself, right? I could just look at y, oh, it's this uncertain, has a certain entropy rate, and I'm going to tell you the x time series, what's the improvement or reduction in unpredictability? That is what x is contributing. That's the motivation behind this. Okay, so let's do some examples. Okay. We're going to have two time series, x and y, and they're produced in the following way. So x is just a fair coin flip at every time, and we're going to start off y with just a coin flip, and then we produce the future y's using sum mod 2. So these are just binary random variables, coin flips, and I just sum mod 2 to get the current value. And if you go through, and I won't detail this, the transfer entropy is 1 bit, right? The transfer entropy, the information flow from x to y is 1 bit. So 1 bit of information has been transferred from x to y. Well, let's check this out. So I'm going to give you two different arguments. So if you look at that system, the way y, the time series is being produced, you can show that y's output is independent of y's past. They're just randomly distributed. And it's only when I get to see x's value, I know what the contribution is in that sum mod 2, that you conclude that that 1 bit of information in y is actually coming from x. So this is the information diagram analysis of that. But now let me give the argument a complementary way. So I now look at x's past, and you can show that it doesn't share any information, no mutual information with y. It's only when I look at y's past that I see that there's a bit of information shared. Both of these analyses can't be true. Right? So what's this saying? It says the information in y's present does not come from either y's past or x's past, but comes from both of them simultaneously. So the transfer entropy said there was 1 bit. Nope. Coming from x. Nope. The point here is that this particular pair of time series, the information in y comes from both y's past and x's past together, right? So the transfer entropy is grossly overestimating the information flow. It's not really due to the transfer entropy is positive, but it's not due to information flow. What's happened is there's a sort of non-localizable influence. In other words, there's a conditional dependence. The pairs of variables appear to be independent until I add the third variable in, and that induces a dependency. Usually we're familiar with thinking about conditional independence. I have two variables, and I can render them independent when I find a third. This is exactly the opposite, and it's absolutely critical to this, and it's what the transfer entropy misses. And we can kind of keep going on. What's my time? I'm blabbing too long. Oh, good. Okay, great. Okay, so we can. There are more examples of this. So we have two fair coins here, and we sum mod 2 again to get a third. Go through the calculations. There's no transfer from x to the output or y to the output, even though they're here. There's a formula. Y and x are determining z. There's no transfer entropy. In fact, you can go through, let me not do the information diagram. You can show you have 3 variables, x, y, and z. They're all pairwise independent. So what's going on here, right? There's really, the transfer entropy sort of builds in an interpretation that misunderstands conditional mutual information. this conditioning is not subtractive. What happens is that this kind of mutual information, I'm looking at how much information is shared between output and input, or x and y, given z. It's what does this dependence between x and y look like, taking into account z. And it can either render x and y independent or render them dependent. It depends. So the problem actually is not with the transfer entropy. It's not the mathematics. It's not even the numerical values. I could give you 10 papers in neuroscience looking at spike trains. It's not even that the numbers are wrong. It's the interpretation. So this is actually one of the Achilles heels of information. It's very attractive. I just argue for this kind of intrinsic semantics of information that's actively stored and all that. But you have to be really careful in drawing structural or causal interpretations. And unfortunately, the transfer entropy, there's a vast literature out there, shall we say, that needs to be revisited. This is bad, really bad. So kind of embarrassing, maybe embarrassing for us, so as advocates of this sort of thing. Another way to think about this is kind of a very nice framework introduced by Paul Williams and Randy Beer called the partial information decomposition. And they have a kind of a logic gate. They have inputs to a logic gate and an output. So kind of under that assumption, you can think of x and y's past as being the inputs, and there's something that happens to produce the present y, the output. And they break this down, this kind of mutual information, they break down into a redundant kind of information, mutual information, that both variables contribute. There's information coming from just one variable or the other uniquely, and then there's this fourth component, key synergetic information. Information is only showing up in the output because both inputs are contributing. And that's the previous examples were constructed exactly kind of push on this point. So in other words, the transfer entropy conflates these two things. The transfer you can show, it's the sum of those two things. So it's mushing those things together, and therefore there'll be contexts in which a causal interpretation is just wrong. So yeah, don't conflate conditional independence and conditional dependence, and certainly you don't want to conflate unique information from synergistic information. These are different architectures of information processing. So, open question. What is information flow? I don't have an answer for you. Really, this is important. Go figure this out. I've been working on this stuff for an incredibly long period of time, and to be here in this year thinking that we don't have an actual consistent measure of information flow, it's something. It's an opportunity. So I can be kind of critical of transfer entropy. That's fine. This is an interesting, easy to state problem. The different groups now actively working on this, and it's more subtle than we think. One way to think about this is that our training in physics has given us certain notions of structure and correlation that are inadequate to many, many, many complex systems. So this is an opportunity for pattern discovery. What is going on? It's really a meditation on what we think correlation is. What is correlation? Well, you go to the board, you start writing down all these two-point correlation functions, even the connected correlation functions. Total mess in StatMech, as far as I'm concerned. And they don't have a built-in semantics. It's just... So this is kind of a good thing, right, to have like big questions. It's still open like this. It's a real opportunity. So obviously, I encourage. I think I'm going to try to wrap things up so we have some time for discussion. Let me just say there's some more recent work with Ryan James, who's the primary person on the transfer entropy critique. It gets worse. So we've gotten kind of a cranky, curmudgeonly mood in Davis, and we can now systematically create various kinds of joint distributions that frustrate pretty much all Shannon information measures. So this open problem I just meant, it's really open. So let me not go through this. There are ways of building these various kinds of joint distributions over 4-letter alphabets. They have different kinds of pairwise only or three-way. You can go through, and this just kind of explains how they're structured. Let me not go through that. There's a whole family of these distributions we can make that all have the same information diagram. So in any dimension, we can create these things that the information measures, this wonderful calculus I just introduced, beautiful information diagrams that help us find new ideas, totally opaque to these even simple dependency structures. You know, quick connection to quantum. No wonderment. No, that doesn't. I'm not surprised, having said this, that entanglement is difficult. Seriously. We don't know what we're talking about, even classically. Well, we have a number of colleagues in computer science that are leading a whole new revolution in big data, data mining, these fantastic machine learning algorithms, deep learning. So let's take a look at what the best machine learning algorithms today say about those two distributions I just flashed by. I'm going to build a Bayesian network of those. Surely that'll capture the dependency structures, pairwise. For both of them, this is what Bayesian networks produce. This, I like this diagram because it's so simple. I see in this the future of big data, the way it's currently being pursued. All right, I'm editorializing, but I'm also half serious about this. You know, so Ryan went through 24 plus of all the various kinds of information measures that people have produced, nominally either directly said, we can determine the causal structure of your complex system, or they kind of hinted at this. So here you go. Just all of these things. And you'll notice that there are these two, pairwise and three-way distributions. They're all the same except for actually three. This is the Koch, corner Koch common information, and then these are these, well, you can read it here. Intrinsic mutual, the language is actually kind of fascinating. Co-information, dual total correlation, Gotch corner common information, Wiener common information, exact common information, functional common information, MSS, I can remember what that, reduced intrinsic mutual information, the extropy, residual entropy or erasure entropy, the perplexity, disequilibrium, it goes on and on, right? It's like everyone gets to invent their own word and come up with some permutation of H's and I's and bars and commas and semicolons, and it's a blah, right? So it just pretty much kind of missing these dependencies. More opportunity. The William and Beers partial information decomposition actually does pick up for those two cases. That they have a different dependency structure. This analysis of this kind of mutual information interpreted as a particular input-output relationship. You have to think of X, Y, and Z not democratically, but X and Y are feeding Z. But then we know how to construct other distributions that foil this too. So we're in a really bad mood these days. So okay, let me kind of close up real quickly here. So that's kind of the, basically, message. Shannon information measures, what I first started out sort of extolling the virtues of, and I'm not entirely pessimistic, but at least this is sobering. Can't pick up these simple dependency structures. Watch out. Be very careful what you're using these tools for and what kind of conclusions you want to draw from them. Doesn't mean, in particular, that transfer entropy is not important. In fact, in some recent work in this fluctuation area, non-equilibrium fluctuation theorems, there are various settings where one derives the transfer entropy, and it has a meaning in that context. But as this general tool for running around and analyzing complex systems and their dependency structures, you have to be careful. So real quickly, just to kind of end up, at least consistent with the theme of me puzzling over what we're doing, I want to talk just very quickly, although there are going to be other talks here and there are posters out on this topic, this sort of ambiguity of simplicity, comparing how classical theory and quantum theory view complex systems. And this is implicit in a number of works folks have done here. So what do I mean by a process is simple? Well, one thing I've been using for a while is the amount of information stored in the effective states of a process. So imagine we have some time series. And then from that time series, we can build up the effective states by calculating these conditional distributions. So we say that two pasts are equivalent when conditioned on those particular pasts, the future looks the same. And this actually goes literally right back to that geometry of a time series thing that we developed for fluid turbulence. It's kind of a discrete symbol version of discrete time, discrete symbol version of that. Anyway, so once you find these causal states, these equivalence classes of pasts, you can ask how much memory is stored. And the kind of argument here is that these causal states sort of are the relevant summary of the past, optimal relevant summary of the past, for optimally predicting the future. So that's these epsilon machines are optimal minimal predictors. And there's a calculational procedure for calculating them. You can do this from data in your theory, write down your Hamiltonian. If you're a good calculator, you can get your conditional distributions out and find the causal states. And so we have these notions of process A is simpler than process B when the statistical complexity of A is less than that of B. Or actually, my original motivation was a definition of emergence. This goes back 30 years. We can say that some system is emergent. Think of the BZ reaction. You start with this random distribution of reagents in your Petri dish, and then they start to oscillate, target patterns form, and it becomes more structured. It has more memory. So the idea is that the process is emergent is when its statistical complexity, the amount of information it stores at later times is larger than earlier times. Okay. So now, there's an information theoretic interpretation of the statistical complexity. So you imagine you have your process here. Now Alice wants to tell Bob how to predict the time series. And the question is, how much information does Alice need to send to Bob so that he can do that? And the punchline, without a derivation, is that it is the statistical complexity over a classical channel. So what happens if you have a quantum channel? And this brings up, and I hope we're going to hear a whole set of talks on this, a way of constructing an optimal quantum channel from, let me drop optimal, constructing a quantum channel given a classical process, right? So the problem setting is I have a quantum channel. All it can do is transmit qubits, but I want to transmit a classical process from Alice to Bob such that Bob can continue predicting. Okay, simple set. So you can form what's called a Q machine, although there are a couple different constructions. It goes back to our various groups here, looking at the causal states and the words that follow various states, and then the kind of the transition probabilities, roughly speaking, show up here as weighting factors, form the density matrix, and then we have our measure of quantum memory through the Holevo idea, interpretation of von Neumann entropy. We can just look at trace rho log rho, and that is our CQ, the analog of C mu, and you can show, people have shown that CQ is upper bounded by the classical memory. Good. So we have measures of how structured things are in the classical domain C mu and in the quantum domain CQ. Well, so let's compare. So here we have in the classical domain, process A is more complex than B. And when we look at their quantum versions, A is more complex than B, right? They're both less than the classical, but their ordering is preserved. However, they're rather common systems where, in fact, the ordering changes. So this is kind of the punchline, which we've all been staring at for a while. A is more complex than B classically, but B is more complex than A quantum mechanically. Huh? Well, we have an abstract proof of this, but people don't like that stuff. So you could also calculate your favorite spin system, long-range correlations. Nice poster or two out. Should take a look at. So just here's the plot of for a spin chain as a function of temperature, C mu, the classical complexity, and then CQ in green here. And you notice that this is sort of monotonic. C mu is monotonic in temperature, but CQ isn't, and that leads to this ambiguity. In fact, there are ways of showing that. One critique of this is, well, your CQ or your Q machine construct, I have a better one, and it would change things. But we have the more general argument shows that any improvement is still going to lead to complexity measures that have quantum versus classical ambiguity. And it's quite robust. The whole regions, now we're just comparing two different spin systems at different temperatures. The whole regions where you take that spin system, a pair of spin systems here, T1 and T2, look at the quantum representation, the ordering is preserved, but there are huge regions in parameter space where that ordering flips. So they don't agree. Classical and quantum theory apparently don't agree on how structured the world is. So much for looking for simplicity in the world, right? This is puzzling. I mean, there's certain elaborations we'll do and we'll push on this, but it seems pretty puzzling, actually. I mean, why? You would have hoped, well, imagine some future where these things are all now quantum mechanical. Isn't this where we're going? Well, one of the most common things we do with these boxes is we analyze data. And very often, we give them various kinds of model complexity metrics. Compare how many terms you want. Should I use 15th order polynomial or 3 order polynomial? All these model complexity terms. In fact, most of machine learning is about complexity control, not overfitting to your data. But now, the claim here, speculation, would be that when we're running on a quantum machine, we're going to have different answers because we don't have the same way of monitoring model complexity. We have different answers. So, problem. So, using information measures to discover organization of complex systems, potentially very, very, very misleading. So that was the first part of the talk. And then kind of the bigger problem, I think, certainly to physicists, given how we've been trained, is that quantum and classical theories simply disagree, and that kind of throws the whole notion, Newton's notion, that simpler theories were better, kind of out the window until further notice. So, again, some of this history I've been looking at, this is a long history of people really enthusiastic, I'm one, about using information theory to study complicated systems. So this is kind of interesting quote. Information theory is very strong on the negative side, demonstrating what cannot be done. On the positive side, its application has not produced many results so far. It has not yet led to the discovery of new facts, nor has its application to known facts been tested in critical experiments. To date, a definitive and valid judgment on the value of information theory is not possible. Oh, well, this is actually from quite some time ago, from 1956. People were having these debates. So there's this interesting character, Henry Quatzler. It turns out he was a American biologist, one of this early kind of group of people with Turing and von Neumann and Wiener and you name it, this kind of interesting Bateson, Margaret Mead, all these people who sort of met at this series of conferences in the late 40s through the mid 50s on cybernetics and information theory, funded by the Macy Foundation, the department store foundation. So they were debating all these things back then. Of course, he was talking about the study of living things and information theory and biology, but somehow I'm just kind of puzzling, stepping back and wondering about what we've been doing. So is this really some kind of deal breaker for information theory? Are we really totally out to lunch when we think about pattern and structure in the world? That it's, I mean, someone, I could see, if outside this room, I could imagine like journalists, which has already happened in some domains, coming in saying, see those results. What he's saying is it's all subjective. I knew it. Science, it's all, this could be bad. I've gone through this before with complex systems, and people even essays in Scientific American, the magazine, whole books, The End of Science by John Horgan in 1999. I know. However, my interpretation is basically optimistic. I think we can, solve these things. We need these tools anyway, and there's just a tremendous opportunity here. So, go forth, invent, discover a measure of information flow. Thanks.